Hello there everyone, this is DB2. We are entering chapter 13. Greetings from this bridge of the Star Destroyer. The focus of this particular chapter will be on the evaluation of query plans. We've been talking about the individual nodes, the individual operators in these query plans and how, grouping or sorting or joins would be evaluated. But this chapter is about the orchestration of complex plans of all these operators that act together to implement the semantics of maybe complex SQL query. And there's some interesting observations to be made here, in particular since the choice of strategy between MonetDB and PostgreSQL is entirely different, with very interesting consequences for both of these systems. So let's dive right in. All right, chapter 13, plan evaluation. All right, so what we would be looking at is query plans. Well, query plans of the type that are not consisting of, say, one or two operators, but complex query plans in which a number of operators have to work together to implement the semantics of a complex query. We have to coordinate the execution of these operators. We have to execute them in the right order. We have to pass intermediate results between operators so that at the plan root we can finally grab and then return the overall result of our query evaluation. There's quite some questions to be considered and answered here. If you recall, the query plans that we were looking at, they had the shape of operator trees. So, one question that immediately comes to mind is who's driving the evaluation? Is data pushed from the leaves upwards the plan towards the root? So, at the leaves of the plan, we will obviously have operators like sequential scan or index scan that really draw from the data sources that we've prepared in our database system. From these sources, is the data pushed towards the inner nodes and then pushed towards the root so that the root can then finally emit the result? Or would the initiative be located at the root of the node of the plan? The root of the plan that then requests its subordinate plans, its upstream plans, to deliver results for final emission. Then, so is the root driving the entire plan? The root is tasked with emitting the result. It cannot emit the result if the subordinate plans have not delivered the intermediate results. So the root of the intermediate plans ask for their results, and these plans will then forward these requests for data to further child plans further down the tree until we hit the leaves. So in this scenario, the control would be at the root node, which tries to pull the data up towards the root of the tree. All right, so these would be two entirely different strategies to drive the evaluation, and we will see that indeed MonetDB and PostgreSQL are instances of either the one kind, MonetDB, or the other kind, PostgreSQL, and there are some interesting consequences here. Also, what data would be passed between the nodes? What data would flow on the edges of the plan trees that we've constructed? Well, would we ship entire buds or entire tables of data from operator to operator? So one operator does its entire job and then will deliver an intermediate table, or maybe only one column in the MonetDB case, and pass that entire column on to its parent operator? Or will we operate row by row and pass only single rows across these edges, so that if one operator demands the next intermediate result, that it won't receive the entire table, but it will receive the next row that would belong to the intermediate result. Sometimes that may be sufficient for an operator to continue its operation and then already pass one row upwards the plan. So this is a different strategy, a strategy that talks about data granularity that is passed across these edges. And again, we will see that MonetDB and PostgreSQL are at the opposite ends of the design spectrum here. Right. And then there's the question of, well, if we execute such a plan, will it execute completely? Will it deliver the entire result in one shot? Or will the plan be able to just deliver the next result row, and we could demand the next result row from the plan in an iterative fashion? Please deliver the next result row. Please deliver the next result row if there is any next result row. That would give us some control at what speed and at what and what investment in space resources, for example, we evaluate such a plan. And again, MonetDB and PostgreSQL at different ends of the spectrum in design here. So I think it should be quite interesting to see the differences between both systems in this particular chapter 13. To have one concrete plan to talk about and a concrete query, just like it's the philosophy of this entire course, let's look at particular sample queries and then trace how the system will cope with these. Well, it will be no different in this particular chapter. We will look at query Q12, all right, probe query Q12, and of course its plan, because our focus is on the evaluation of the plan for Q12 here. Right, so that would be Q12, and it should be rather familiar. It's an equi-join between the one and many table that you've discussed so far. Then a subsequent grouping operation that will just count the size of the groups, the number of rows that have been placed in each of the groups, and then order by the grouping keys in descending fashion. So the largest grouping key would be the top row of the result. The smallest grouping key would be located at the tail of the result. All right, so Q12 is not a particular complex query, but it's also not trivial. The plan that it will that we need to implement for this particular query will consist of probably the following operators that make up the entire semantics of the plan. So we will of course have sequential scans that access the rows of the many and one tables. We don't consider index support here. Right, both these sequential scans will feed their rows into a join operator, a nested loop join in this particular case, that will implement the from where join pair here in the SQL query. From that nested loop, we will feed the output into a hash-based aggregation operator that implements the aggregation by O.A and the counting. All right, and finally, when we are done, well, we can then finally sort the output to implement the semantics of the order by clause here. All right, so the tree-shaped plan that will generate will be generated for this particular query would then probably look like this. We will start out the plan at the leaves at the data sources, where on disk we will find the instances of the many and one tables. And we would start out with these sequential scans here, which would pass the results. Indeed, I have shown the intermediate results of these operators here as annotations on the edges of the plan. Intermediate results flow in the direction of that particular arrow here. All right, so both sequential scans would pass their intermediate results into the join operator here at number 3, which would do its job and then produce rows of this particular size. You see that the join predicate OA equals MA has been implemented. For example, this particular row did not find a join partner. This particular row indeed found 2 join partners, so this is what we see in the intermediate join result here, which would be then passed on to the grouping by A. All right, so 2 groups will be constructed of size 1 and 2 rows, and well, finally we would sort in descending A order, so the grouping key 3 with the maximum 3 value will be found at the top of the result. So that would be one particular plan that we could look at, and we could try to answer all these questions. Well, is operator number 5, the root, is driving the plan evaluation, will the operators 1 and 2, the leaves, will they push data into the plan? And well, yeah, how is everything orchestrated? In which order are operators evaluated, and so on? So indeed, the numbers 1, 2, 3, 4, 5 already hints at one particular evaluation order, but this will be an evaluation order that fits one system but not the other. So we will see that MonetDB, which we will discuss first here, will indeed follow this particular evaluation order, but it will be different for PostgreSQL. All right, I think the stage is set. This is the sample query, the sample plan that we would like to discuss in the following. All right, so as I just said, let's look at MonetDB and the MonetDB plan evaluation strategy first. Indeed, MonetDB follows a strategy that is called full materialization, and I think the name says it all, right? Indeed, each operator in such a MonetDB plan, which we know is equivalent to a MEL program, in each of these programs, evaluators operate on their entire inputs, do their entire job, and then generate their entire immediate result, which will then pass on to the next operator. The full intermediate results are being materialized. There are points in the plan where we can indeed look at these intermediate results that I've shown as annotations here. These are indeed constructed by MonetDB, and only once this particular intermediate result has been constructed, operator 2, or maybe 1, will finish its job, and only then operator 3 will perform its thing. All right, so what we've just described is this strategy. Leaf nodes are indeed evaluated first, and well, downstream nodes that are located towards the root, will then consume the buds, the entire bud that have been generated by these leaf nodes, or in general by their child nodes. The root operator, of course, is evaluated last. Right, so if you look at these particular plan trees, and we will see in a second that indeed MonetDB internally first constructs such a plan tree, which would almost look exactly like what we've seen here on the slide. And well, that plan tree would then be linearized into a MEL program. A MEL program is a sequential program, as we've seen. So we need a linearization of this tree-shaped operator data structure. And the answer to that is, well, simply follow a post-order traversal of that query plan tree to derive at a sequential execution order of the operators in this particular plan. That sequential order will be the instruction order inside the MEL program. And well, that defines what would be a leaf node and what would be a root node. All right. Right. And who would be evaluated last in this particular case? Okay, so each operator indeed produces and consumes entire buds, and everything in between is fully materialized. Right. So, well, this is a prerequisite to the operator evaluation strategy that has been implemented inside MonetDB. We know that the internals of each operator is designed as very tight code loops that process entire arrays of data, entire columns of data. To make this happen, well, that entire array has to be materialized in memory so that we can iterate over this region of memory without being interrupted by, well, the execution of our child nodes or something. When we are inside the code of one particular operator, we will stay there, and we operate under the assumption that the entire input has been materialized as an in-memory array. This leads to all the salient properties of these tight code loops that we've discussed so many times already. Instruction and data locality. Data locality because we only reference data that is in one particular input column. Instruction locality because we are operating in these super tight code loops. There will be predictable memory access. If we are lucky, there will be just sequential memory access across the input, but the input array. And all of this amounts to a very efficient and very speedy execution on modern CPUs. Of course, we have to be prepared to cope with the size of the intermediate results. And those intermediate results may be substantial. They are, of course, not substantial in the toy plan that we've just seen on the previous slides, but they may be substantial in real-world query execution plans where really bits of substantial size are to be processed. The system has to be ready to really materialize these intermediate results in RAM. If that is not possible, because the size of the intermediate result, consider the cross product of two large bits, for example. If the size of the intermediate result will not fit into RAM, well, the OS will do its job. It will do OS level memory paging, which will ultimately lead to disk I/O. And well, that's why even a memory-based database system, a main memory-based database system like MonetDB, may incur quite some disk I/O because of virtual memory management. Right. Okay. So let's have a quick look at well, the query Q12 in MonetDB, its algebraic plan, its tree-shaped plan, and the resulting mul program there. All right, so let's switch over to the terminal here. Here we go. This is a MonetDB session running in its SQL mode. So let's quickly prepare the sample tables, the one and many sample tables. This is their schema. This is the instances. We have seen these instances before, so bear with me. I will not further elaborate on these. You see that we have the two A columns here, carrying integer values in both tables, which will serve as the join criterion in our sample query. Well, and here is our sample query. This is just the query from the slides verbatim. What you see here is that I've prefixed this particular query with the plan keyword of MonetDB. Well, this is similar to explain, but what we will see here is indeed the algebraic tree-shaped plan that MonetDB has prepared for the evaluation of this query, and not directly the sequential mul code. So we can use the plan prefix here to have a look at the algebraic tree-shaped plan. So let's do that. We haven't done that before in the course of DB2. All right, so that would be the algebraic plan for this query Q12. So I apologize for the output, which looks rather scrambled here, only because my terminal is not wide enough. So I can only recommend that you replay the evaluation of this query and the generation of the plan on a terminal of appropriate width if you follow at home. All right, so but what we can see is that what MonetDB plans for here is indeed the tree-shaped plan that we have considered on slide 2, I guess it was, or slide 3. All right, right. So well, the plan starts at the leaves, which are of course located in this inner mode nesting here in this text-based representation. The plan starts with the evaluation of sequential scans over the one and many tables. The one and many tables have each two columns each, but as you can see, well, the scan will only produce the relevant columns here, the A columns, which are the only columns that are being referred to in this particular query. So there's indeed some optimization going on already. We will only be required to access the A column butts and can leave aside the B column butts in both tables. But sequential scanning goes on first. Then there will be a join that will consume the output of these two sequential scans. And knowing that MonetDB follows full materialization, we know that indeed the system has to prepare intermediate RAM, intermediate memory, to hold the intermediate results of both of these sequential scans. We can only hope that the available memory suffices to hold these intermediate results. The join, probably a radix cluster join, will then do its job. We can even see that one particular column has been designated as the hash column here. So indeed there will be hash table construction going on. That's no surprise. We know about the join strategies that are implemented inside MonetDB. After the join, we will see the group by, and the group by, of course, is referring to the A column as a grouping criterion and it will also generate the count, the size of rows inside each group. Okay, and then there's two final projects here. There's this first project which will perform some renaming of columns here, and then there's the final project that if you scroll down and look at its arguments, at its parameters here, that particular project will generate a two-column result table. One of these will be named A, one of these will be named hash sign or number sign, the size of the groups, and it will perform ordering. This is the ordering criterion. So ordering is represented in terms of project here inside the MonetDB plans. This is indeed the ordering criterion. By default, I think this should be a descendant ordering. If we change this into an ascending ordering, let's try that. Then this is the same plan. Yes, indeed. We see that, well, the ordering criterion now indeed is ascending. All right, so we see that the topmost operator indeed implements the sorting in the MonetDB case. So that would be a tree-shaped representation of the plan that has to be performed. Now, according to MonetDB's evaluation strategy, we will linearize this tree-shaped data structure using a post-order traversal of its nodes. That will lead to a sequential ordering of all the nodes here in this particular tree, and we will use this ordering of operators to construct a sequential mal program. Okay, so let's see whether this is indeed what happens. So, well, this is the same query again, but now instead of outputting the plan, we will just output the mal program like we have done so many times. Explain. All right, so what we end up with, of course, is the sequential mal program. Let's scroll to the top of the program. If we indeed follow the post-order traversal of the plan tree, then we should find the leaves of that plan tree first in the sequential program. And indeed, this is what you find. If you look at these three instructions, they indeed implement the sequential scan of the one table, but only of the A column. All right. And then there would be instructions to generate or perform the sequential scan of the many table, the A column of the many table. Indeed, this is what happens here. So these would be the two nodes that would be produced first in a post-order traversal of a tree, and indeed they are found first here in this sequential mal program. There is some opportunity for parallelism here. Well, let's postpone that for slide 5, but let's continue in the post-order traversal of the tree here. All right, so the next thing that would happen in the post-order traversal of the tree is, or the next node that would be reached in a post-order traversal of the plan tree would be the join node, and this is indeed what is being performed here in this mal program. Then there is some post-processing regarding the join bar that is produced by this algebraic join, and then the next thing in the post-order traversal would be the grouping. And well, the grouping would perform a grouping, would output the grouping but, and that would be applied here. And then we will perform the aggregation. So grouping and aggregation builds a pair of operators here in this particular plan. So that would be grouping and aggregation done. And then finally, at the top of the plan, as we've seen in the tree-shaped plan that MonetDB has output, there's indeed the sorting going on, which will of course lead to an order index, which is then applied to the required columns. This is the end of the plan, and well, we would be able to construct the result representation here and then return from plan evaluation. All right, so indeed, the algebraic tree-shaped plan has been post-order traversed and then transformed into a sequential mal program, the programs that we have seen so many times already. All right, well, let's switch back to the slides here and have a look at the mal program that we've just seen on the slide in some more digestible form. So that would be the mal program that we have just seen, just with all the identifiers renamed and some structure being imposed on the program. And what we see is indeed the post order traversal. It's a scan of the two relations at the leaf nodes, then the join, then the group by, and finally the sort. This is exactly what happens in the algebraic plan, and thus in the mul program that implements this algebraic plan or tree. And well, as you can see, I've explicitly annotated the data dependencies that are present in this mul program. So you can see that this join operator cannot do its job before the 1A and the many A intermediate buts have been materialized and actually been produced. And these are produced by the many A and the 1A assignments here. All right, so it's clear that this group of statements and this group of statements, it has to come before this algebra join. There is interestingly no dependency between, well, these three instructions and these three instructions. Well, the scanning of the one and many tables are independent of each other, and they could indeed happen in parallel. And there is an optimization component implemented inside MonetDB that determines such non-dependence or such independence between groups of mul statements and tries to schedule these in parallel on multi-core machines. So the parallelization opportunity that is present in this particular plan is indeed exploited by MonetDB if the underlying hardware is able to support that. Otherwise, well, there is data dependencies here that we have to respect. So, well, we of course cannot perform the grouping before the join has not performed its thing. So this is the data dependency here, and everything else indeed is sequential. So we cannot perform the instructions that are listed down here before their predecessor instructions have been performed and their intermediate results have been materialized. All right. So as you can see, indeed, data is passed between these sections of the plan in forms of entire materialized buts. What you see here, what will flow along these edges in this particular plan are always entire buts. And of course, well, the system has to accommodate these and find the appropriate space resources, RAM, to hold these. And well, it depends on the query, but it can really turn out to be a challenge for the MonetDB implementation. And I think we should be able to see that in the upcoming video. I hope you will stick around. See you then. Bye-bye.